This topic of the evolution of airplanes. That is about the movement of people on Earth today. That's what is happening. You don't cross the Atlantic greetings, in one of these boats that took 6 days to cross. Those were steamships. Great improvement over the boats with sails, which will be one of the subjects today, the boats with sails. In any case, don't take airplanes lightly. They may be about transportation, but they're in fact an introduction to the little, let's go concluding part in this course, which is about the design of society and some of the words that are used sometimes incorrectly about that design. Okay, so I begin with a brief review of the main results from the preceding lecture, because they are based on an airplane model that is different than the one that I will invoke today. Last time, we modeled the airplane as being made of 2 parts, the fuel and the engine. That was the simplest drawing of this thing that moves. Not a bad drawing, because the fuel is occupies a big fraction of the airplane at takeoff. Anyway, along the way, we found this correlation between the efficiency of the motor and the mass of the motor, called engine. By the way, motor is a better name for this device called engine. And then raised to an exponent that's compared with 1, but smaller than 1, times the fuel inventory. No, forget about that. That is not. And then we found that the total movement and movement is the origin of the word moment in English. Movement is the product of the stuff and the distance to which it was moved. This is what really costs money. Think about it. It's more expensive to move a big thing. It's also more expensive to move it to a long distance. Get it? And the product of the two is twice challenging. And we found that this product is a constant, h being the heating value, mu g, I defined them last time, and then the motor mass to power alpha times the fuel inventory. And we found, and this kind of finding repeats itself, meaning keep an eye on it's reappearing on the blackboard. We found that the size of the engine scales with the total mass, meaning with the either of them and the sum of the two. The fuel mass scales with the total mass. A few other relations, in fact, even earlier we found that the fuel mass is 1 over alpha, the motor mass, and ... Everything scales together. Big airplane, big engine, big fuel load. Proportionally. It is as if there's only one drawing, and if you magnify it, you get the drawing for the big airplane. If you reduce it, you get the drawing for the tiny one. Assuming they're all jet aircraft, because this kind of correlation for the economies of scale in the design of engines applies to one kind of engine, in this case, aircraft. I mean, a jet aircraft. So that's from last time. What is new today? Today, the topic is about how these things are moving on the surface of the Earth. Oh, incidentally, you like the airplanes, you can do the same thing to trucks on a highway, big ones and smaller ones. That's an exercise worth contemplating. In fact, this is the beauty of fundamental work. You get an idea, you learn how to deal with it, or how to what's the word in English, to how to yield results, and then, that being the case, you're free to try that idea again on another, let's say, group of animals. And then you predict the future of that particular group. So now the new, so today, movers on Earth. And we assume an elemental area. By the way, this is now a large-scale version of the Atlanta airport. It is rectangular. This is what you see when you look on the map of the world. Small territory, large territory, you see something that's two-dimensional. And this thing has two dimensions, L2 and L1. And it is populated by one big mover and smaller movers that we have a hunch here, just like the pedestrians in the airport. The smaller will be more numerous. And the mover is flying long distance. This is the size of it, M1, with speed V1. And then transversely, there are smaller movers called M2. A certain number, we don't know how big, called little n. So the total mass that's moving, so this is total, is M1 plus n M2. One of the lessons you learn in this course starts from the question of what do I need to make the drawing? I told you last time, more than once actually, that what I need is proportions, aspect ratios. One is the shape of the rectangle. So I'll call them degrees of freedom, L1 over L2. The other one is the ratio of these two vehicles. So now I'm talking about vehicles, not necessarily airplanes. M1 over M2. There's another, this is a third degree of freedom, and that is the number of small that go together with one big, the n. So this is the summary of my problem. And by the way, when you embark on an adventure, you have a destination, you have a roadmap, but you also have a plan or a purpose, an objective. In this problem-solving exercise, the objective is the human one, which is to keep this movement going by burning less fuel. It's called economics. Very, very old, like the word itself from Greek. Common sense. This is not, we're not minimizing the consumption of fuel because we want to save the earth today. You just read today's news. April is the Earth Month at Duke. Yeah, no. This is a very old attitude, and it is the one that brought us to this stage of advancement. So, how to determine these with less and less fuel consumption to drive all this movement. And at this stage, it's kind of talking to myself, I invent another small model of each of these movers. And that model, as you'll see very soon, has, once again, two parts, but not the ones that I assumed here. The two parts are the following. The total M, either 1 or 2, is equal to a portion called chassis or empty structure. You weigh it. In fact, they weigh it when they liberate it from the factory. So that's the structure, and then plus the size of the engine or the motor. So that would be the path of the very simple analysis, and the analysis begins with some formulas, a few of them that were written on the blackboard last time. If the movement is to a distance called capital L, then the work required to drive that movement is equal or approximately equal as a factor called mu, the weight of the vehicle times the distance traveled. That's one move. Second, the movement is driven by the burning of fuel. The burning liberates the heat input that's proportional to the fuel consumed times a factor called heating value. And substituting, and from the definition of motor efficiency, which is W over Q, the bottom line is that the work requirement is eta mf and then h, and then the fuel consumption is, I'll just say this, mu weight L over eta h. And at this stage, we invoke one more time the economies of scale that characterize the evolution of engines. So this eta will be C1 and then mass of engine to power alpha. And out of that, meaning out of all of this, comes the conclusion that the fuel consumption, you see it here, varies as mass divided by engine mass. It varies as mass over engine mass to power alpha. However, the engine mass is I was skipping something here, so I apologize for that. I'll show in just a second that this engine mass is varies as the total mass to power alpha. The conclusion being that the fuel consumption is proportional to the engine mass to 1 minus alpha. But I was skipping ahead on my notes. At this stage, I'm returning to this two-part model. So from here, and I go to the fuel requirement, which is MF, and I write that MF equals or varies as mu, meaning mu times weight, and then C1H, and instead of divided by the engine mass to power alpha, but instead of M, I write the model invoked here, which is MS plus ME. I'm interested in reducing this requirement, the requirement of fuel. And of course, I have freedom to do that, to turn a knob. And that knob is the relative size of the two parts in the body that moves, structure and engine. And here on my notes, I did that with the intersection of asymptotes. And here return to white chalk in the limit of small engines. That means I'm neglecting ME with respect to the size of the structure. The fuel requirement is proportional to MS divided by ME to power alpha. In the opposite extreme, which means big engines, the fuel requirement, in other words, I'm keeping ME instead of MS. The fuel requirement varies as engine mass to power 1 minus alpha. And at the intersection, clearly I'm writing MS over ME alpha, the same as ME 1 minus alpha. And that means that the trade-off between those two mass components is happens when they're of the same size. Meaning, just like on the airplane, big engines on big things. In this case, big empty structure. All right, so this is something to keep in mind. Of course, given the fact that these two parts add up to the total, it means that they're all of the same order of magnitude. And so that's worth keeping in mind as we discover. By the way, MF is not only proportional to M to 1 minus alpha, it is proportional to that times L, the travel. So this is an important result. And now comes the fun part. If the object of the game is this product, I'll just write it M to 1 minus alpha times L to be minimized, then minimized with respect to the total mass means to minimize the mass, the fuel. This is the amount of fuel to cover that territory, the one that I erased. In fact, let me draw it again. We had M1 here traveling L1, and we had many M2s traveling a distance of order L2. So the total consumption is the sum of two contributions, M1 to 1 minus alpha L1 plus N, and then M2 1 minus alpha L2. So that is the quantity that costs money, and we minimize it with respect to, meaning subject, to the total mass that is moving, called M1 plus N M2 constant. This is a typical problem of a la Lagrange multipliers. This is the function to minimize. This is the constraint, this group. I'm not going to do that on the blackboard. And what varies is the ratio of M1 over M2. And so the answer is that this quantity is minimal, or in our current education, the kind of ratios that the diversity of ratios in the vicinity of the so-called optimum is represented by this ratio, which is, where am I? M2 over M1 equals L2 over L1 to power 1 over alpha. Simple. Another piece of wisdom. A simple result usually tells a big story. In this case, the smaller, according to my drawing, must be traveling a shorter distance than the bigger. Get it? We already get the idea that this is a drawing of few large and many small, where the small are traveling short and the big are traveling long. I'll get to that in a second. The word for it is hierarchy. And what's emerging on the blackboard, basically from the back of an envelope, is the natural birth of this particular feature in what moves in everywhere: animal migration, human transportation, everything that moves that way. So this is the first answer. We'll turn the page because this is just one of the 2 degrees of freedom. If I substitute this result in the formula for the total mass that's moving on the territory, namely M1 plus N M2, I get M in front, and then actually M1 in front, and then 1 plus N, and then L2 over N1 to power 1 over alpha. We got a result that teaches us what the next question is. The next question is the shape of the territory to be swept by all these bodies with the minimal fuel consumption. And so that's the second. Well, incidentally, something else that before I turn the page, so this is one one consequence of the result shown here. Another consequence, which I better write on the blackboard, is that the amount of fuel minimized at this stage acquires the value m to 1 minus alpha, and then in brackets 1 plus n, and then the length ratio to power 1 over alpha. No, I was looking in the wrong place. The minimal amount of fuel is not equal, it's proportional to m to 1 minus alpha, and then L1 to 1 minus alpha plus n L2 to 1 minus alpha. This is the punchline, meaning the punchline, the first time we say, gee, we won the battle, except that we only won half of the battle. The second part has to do with minimizing this quantity. So, part 2, minimize the above, subject to the area being fixed. And the second move, believe it or not, leads to an even simpler formula, which is that the ratio of those two dimensions, so the result is L1 over L2 equals the number of small movers to power alpha. Showing something that makes sense. The more numerous the small, the longer the path of the big relative to that of the small, or the shorter the path of the small relative to the path of the big. I hope you get the idea that now you know how to make all the drawings, not just one, all depending on this little number called n. And substituting this result into the previously minimized expression, we obtain the main result, which is about the fuel requirement minimized twice. And we'll write it as fuel minimized twice varies as, according to all this analysis, there's a factor of 2 that's meaningless. Total mass to y minus alpha, the number n to power 1/2, and then the size of the territory to power 1 over 2 alpha. Does it make sense? Always ask yourself this question. You get an answer, or okay, from your ability to express yourself mathematically. Does it make sense? Fuel consumption increases, meaning after you scratched your head twice to minimize it twice, it still goes up when the total mass that has to be moved goes up. It goes up when the size of the territory increases. That makes sense. But there is more to this result. What about fuel consumption per unit of mass moved? So we have this twice minimized requirement divided by the total mass inventory, this thing varies as, I'm not writing the other things, as m to 1 minus alpha divided by m, which means m to minus alpha. And this is not a surprise to us because we've learned about economies of scale. A very important conclusion is that at the end of the day, meaning engineering after engineering after engineering, which is responsible for this, minimization ad infinitum in the industry that evolves to maturity, you discover economies of scale. The per unit cost in terms of fuel decreases rather, let's say, steeply with the size of the object that's getting moved. So let's see now. In other words, this thing. So MF minimized twice per unit of mass. Here's total mass decreases with an exponent that's almost minus 1 because this alpha is close to 1. Not bad, huh? Another way of looking at this pleasing conclusion is to ask this, by the way, if this is looks like a loaf of bread, let me draw it like a loaf of bread. Is to put the question a little bit differently. What about the consumption of fuel, minimized twice, consumption of fuel per unit of territory covered? Well, it varies as A to 1 over 2 alpha divided by A, which means A to 1 over 2 alpha minus 1. And this exponent, now to get an idea of how small it is, assume that alpha is, of order 1 but smaller than 1, say 3/4. Let's find out. I didn't do this at home. So 1 over 2 alpha minus 1 equals 1 over 2 and then 3/4 minus 1. Let's see what we get. 2 over 3 minus 1 equals minus 1 over 3. Meaning that there is this is an exponent that's, let's say, of order minus 1 over 3. Saying what? That the per unit area consumption of fuel decreases. One more version of economies of scale decreases as the territory increases, but that decrease is considerably milder, weaker than what we saw in the first version of this exercise. So, conclusion: the so-called the questioning of your own result, but this time questioning it more severely, more deeply, makes you discover lessons from the past. In this case, economies of scale, which is one of the first lectures that I gave in this course. Remember, with the two tubes in parallel, opposing greater obstacle to fluid flow than a single tube in size equal to the sizes of the first two. To say that we've killed this problem completely is so we know the ratio m1 over m2. We know the other one, L1 over L2. What about n? Turns out n is about the movement of all these things, But that movement has a particular drawing, which in this portion of the blackboard I did not volunteer. I only drew a long line for the path of the bigger object. And to find out the n that allows you to decrease that fuel requirement a third time, you have to imagine a certain number of drawings, each different than the other, with respect to the path of these objects. In a PDF of this paper, which I will provide to you, there are 3 of these drawings, and the first 2 are these. I assume they square territory, so this is A and B. A square territory with only 4 small participants, each participant coming from the center of the little square. In other words, each small participant of size M2. And the first drawing, the path of these small things is shaped this way. In other words, 2 of them come together to travel as 2m2, to travel down, and then that number is doubled coming from beneath into 4m2, exiting as 4m2 here. 4m2. That 4m2 is the big m1 that we had invented earlier. So, and this kind of movement, using the formula for the total fuel consumption minimized twice, actually in this case, you use the original formula, which was m1 L1 m1 to 1 minus alpha plus n m2 1 minus alpha L2. You arrive to a particular fuel consumption called MFA. Another way to connect all these movers into a single one that leaves the box is to make them flow like a river basin that collects all of them as the big river or the trunk of the tree. So we have M1 here, then, M2 here, and then 2M2 until all of them yield 4M2. And this arrangement, so this is like a pedestrian work with algebra. And you find another measure of fuel consumption, MFB. And then you compare the 2 estimates, as you'll see in my PDF, and say, well, the design with a trunk is more economical. Of course it is, now empirically, because everything that flows has a big river that collects. Incidentally, the on an average, meaning statistically, every river that you see is the result of 4 next size smaller rivers. This is like a mother made by 4 daughters, not 2. So when you hear that everything in the world is dichotomous, from pairing, or every big thing flows in the delta as bifurcation, that's true for small movers, laminar flow. But big ones flow this way, or they coalesce, or they separate as 1 to 4. You don't see this number 4 because the map of everything that flows on Earth is kind of complicated. But of course we have departments of geology and hydrology that are very well equipped to figure out these days with computers the average number of tributaries to a significant river. So this is the direction in which to continue to skin this cat and find out how the design, how the drawing, which is free to change, allows you to decrease the fuel consumption even more. So 2 cries of victory from the previous, what I erased, leading to one that's, let's say, even more courageous and not ready for completion in the little time that I have left. Any questions? We'll come back to this kind of thing because fuel consumption costs money, and in order to have a movement, the mover must have wealth. And I'll leave with you the silent aha that the movement is clearly hierarchical, or with a formula earlier that the smaller are many, the big are few, and hierarchical is the consumption of fuel, and then hierarchical should be the distribution of wealth. And that sort of hunch from the back of the envelope led me to checking the economics literature to figure out that, in fact, that is what it is. That sort of one-to-one relationship between hierarchy in fuel consumption on the territory and hierarchy in wealth on the same territory is known, but not given the proper attention